it's Gleason or something. Let me try this. Come on. That's it. Yeah. Simple geometry.
Okay, so we've had a little bit of a break since our last class lecture, so let me try and kind of recap where we are. So we started talking in the last lecture that we had about medium access protocols. And specifically, we're talking about randomized access. And within that, even more specifically, about slotted aloha. So let's recap what that is. So the model we're looking at is that there are n backlog transmitters. So each will send a packet at each slot independently with probability P. And we first looked at the throughput for this problem, and if you normalize the throughput, it's basically the expected number of packets received per slot, and the number of packets received in any given slot is either 0 or 1, and the only way in which you can receive one packet is if exactly one transmitter transmitted. So basically this ends up becoming, because it's basically a Bernoulli random variable with either 1 or 0, the expected value is just the probability that it's 1, right? So the number of packets received is a Bernoulli random variable, i.e. 0 or 1. and therefore expected value equals probability that one packet is received. And the only way to receive one packet is the probability that there's only one transmitter sends. Right? Because if nobody sends, you're not going to get the packet. If more than one send, it's going to be a collision. So either of those is going to result in a failure of packet reception. The only time you can get one packet is for exactly one transmitter to send. So this is actually why the expected value, the throughput, is equal to that probability. Right? It's because we're talking about a Bernoulli random variable. So we said that probability, or therefore the throughput, is all the different ways, n of them, in which exactly one of them transmits and all of the others do not. That's the throughput. And we said that this is maximized. We took the derivative of this quantity with respect to p, set it equal to 0, found what's that point, and we found that it's maximized when p star is exactly 1 over n. Okay? And therefore max throughput equals, substitute this in here, 1 minus 1 over n to the n minus 1. And we said that as n gets larger, this throughput tends to 1 over e. So it's roughly 36%. And visually, the way that might appear is this is the probability p, and this is your throughput. Then eventually, it kind of, as you have larger number of users, it kind of settles into this point where this is your p star equal to 1 over n, but this maximum value is about 36%. Okay. So 36% utilization, depending on how you look at it, is either low or high. It's kind of low in that you're giving up 60-some% of your throughput to collisions, basically, right? On the other hand, it's kind of high when you realize that this is independent of n. You can have thousands of users just use slotted aloha, and you get a constant fraction of the link's throughput without any additional coordination. So from that perspective, it's a pretty amazing result that regardless of the number of users, I can guarantee a minimum throughput of 36%. Okay. So yeah, so depending on how you look at it. So this, of course, is the total throughput. The throughput for each individual user in each case, in whatever the case would be this quantity over n. So this is the maximum total throughput per node throughput. In this case, is simply 1 over n times total throughput. This is because the system is completely symmetric. Everybody gets the same throughput as everybody else. So all n users put together, their per node throughput adds up to the total throughut. So each of them gets 1/n of the total throughput. So even though the total throughput remains constant, of course, the per node throughput will go to 0 as you increase the number of users. There's no way for everybody to get a constant fraction of the system. Okay, so that's the basic slotted aloha. That's really all we're going to say about the basic slotted aloha. But the question we were starting to ask was, what if different users want different throughput? And the extension of slotted aloha that kind of handles this case is sometimes called PI slotted aloha. And for example, let's just consider 2 users. So they will transmit with probability P1 and P2. Now, by definition, the 2 users, because they have different probabilities of sending their packets, may not get the same throughput, so we have to give them different variables to describe their throughput. So the throughput for the first user would be the probability that it sent and the other one did not. So it'll be just P1 times 1 minus P2. And the throughput for the second user would be the probability that it sent and the first one did not, which is this one. And so in general, if you try to look at the throughput values that the two users would get, you would trace out, we said, a whole throughput region where, let's say this is T1, this is T2. We know extremes that are possible. So certainly it's possible to get all the throughput to user 1 and 0 to the other, so like 1, 0. Or you can get 0, 1 by simply allocating, for example, P1 equal to 1, P2 equal to 0, in which case T1 would be 1 and T2 would be 0 and vice versa. We also know this point over here where there's exactly two users, going back to our statement over here. If there's exactly two users, the total throughput would, if they both sent it probability 1/2, 1 over 2, would be 1 minus 1 over 2, which is a half, to the power 1, which is just a half. It would be a half. And so each of them would get half of that, so we get a fourth and a fourth. So there's another point here, which is a fourth and a fourth. So we know that that's also achievable. So the question is, what does the whole throughput region look like? And it ends up looking something like this. And we said that every possible pair of throughputs would lie under some curve, and it's sort of this outer boundary is sometimes called the Pareto saturation throughput region, Pareto boundary, or Pareto boundary of the saturation throughput region. So this boundary is important because anywhere in the interior of this region you could have done better. There's some choice of P1 and P2 that you could have done better by being at the boundary. And the last time I just mentioned this result that at the boundary, P1 plus P2 equals 1. That somehow all of the points on this boundary correspond to setting P1 and P2 in such a way that they add up to 1. Alternatively, in fact, goes in both directions. If you choose any P1 and P2 that add up to 1, you would find yourself somewhere on the boundary. And in fact, both of these points at the extreme as well as the one in the middle also satisfy this condition, because you get this point by having probability of 1 for one and 0 for the other, likewise for this, and this you get by setting both probabilities to be equal to a half. And in general, let's say you did like a quarter and 3/4, or 2/6 and 4/6, or it's 1/3 and 2/3. All of those points just lie somewhere else on the boundary. Okay. So can we actually prove this? Why should this be true? Right? For the two-user case, we'll just do first principle derivation for this boundary. Okay. For more than two users, it does get complicated to derive it exactly. There is a paper I will point you at where this result was derived earlier and a few years ago also generalized to CSMA. So what are we trying to do? So one way to think about our problem is we want to derive this saturation throughput region. So one way to look at this region is that for every choice of T1, if I say that I'm setting my throughput for the first user to be some number, what would I like to do in order to be at the boundaries? I would like to maximize T2, right? If I say, for what value of the probabilities can I maximize T2 subject to T1 being a certain value? And if I did that for different values of T1 going all the way from 0 to 1, I would trace out this whole curve. So if I solve this problem for T1 equal to 0, I would get that T2 equals 1. If I solve the problem for T1 equal to 1, I would get that T2 equals 0. If I solve the problem for T1 equal to a quarter, I would get a quarter. Right? But if I did it for every value of T1 and maximize T2, I could trace out the whole curve. So that's the idea. So sort of the idea is maximize T2 such that T1 is some known constant. Let's just call it C. Now, what is T2 and what is T1 and what is this relationship going to help us with is these definitions that we have for T2 and T1. So we want to maximize the probability of 2 times 1 minus P1, subject to some constraint that tells us that P1 times 1 minus P2 is equal to this constant value that we chose for the throughput. So, I mean, I said T1 equals to C here. What I'm doing here is just calling in that constant T1. I'm simplifying our life a little bit by avoiding an extra constant. But, you know, it's just rewriting it this way is fine too. Actually, let's use C. Let's use C. Simple enough. Okay, so this second relationship basically says that whatever I choose for P1, P2 is going to end up being fixed because of this constant. Okay, so this implies, for example, that P1 can be rewritten as C over 1 minus P2. Once I fix T1, then there's a relationship that's established between the two. Let's put this back into our first equation. So I get maximize P2 times 1 minus C over 1 minus P2. So if we can expand this, maximize 1 minus P2 minus C over 1 minus P2. Debating if I should go the other direction might be a little bit easier. So this is P1 is C over 1 minus P2. I think we'll work it out. Let's just go with this. So multiplying this out, I get P2 minus P2 square minus P2C times 1 minus P2 inverse. So now what are we maximizing over is P2, because if whatever P2 I find to be the optimum point, I can figure out P1 from this relationship in this case. So bear with me a second. Let's try the other substitution also and stare at it for a second before we proceed to solve this. So basically, this is an equation in one variable. Taking the derivative, setting it equal to 0 would tell us P2. Let me just see if it simplifies just for a second if we took the other substitution. So the other substitution would be 1 minus P2 equals C over P1. And in this case, the benefit would be to rewrite P2 as 1 minus C over P1. And so you could also instead try to maximize this quantity, 1 minus C over P1 times 1 minus P1. Is that any easier? Seems about the same, but let's work it out. So this is 1 minus P1 minus C over P1 plus C which, if P1 is not 0, could be written as P1 minus P1 square minus C plus P1. Right, so now the maximization is over P1. Okay, so these are equivalent problems. The one we looked at before here is maximizing with respect to P2. Here's maximizing with respect to P1, but it's really the same problem. This one looks a little bit easier for me to work with. Am I leaving something out here? So C, right? Yeah. Divided by P1, yeah. This looks slightly simpler, but may not be that much different. So that's the same as saying right? Inverse. All right, let's bite the bullet. We have to pick one of these two to work with. I'll pick this one. And let's proceed. So we want to work out the derivative of this. So let's keep the first part constant, take the derivative of the second, keep the second part constant, take the derivative of the first. So if we do derivative of this term over here, let's just call this some function of P1, right? Derivative of this fp1 over dp1, set it equal to 0. So this is the operation we're trying to do. So we'd get p1, or implies p1 minus p1 squared minus c plus cp1. Take the derivative of this, what do we get? Times minus 1 p1 to the minus 2, right? Plus, keep that constant and take a derivative of this, so we get 1 minus 2p1, derivative of the constant, that's 0, this is plus c, times p1 to the minus 1. Okay, so we get, and all of this is equal to 0. So we get p1 minus p1 squared minus c plus cp1 over p1 squared plus 1 minus 2p1 plus c over p1 equals 0. So take p1 squared as the common term. Plus p1 minus 2p1 squared plus cp1. Right, and we want this to be equal to 0. So of course the denominator has nothing to do with that. We can just focus on the numerator. Hopefully some of these terms will cancel out. A little disconcerted that they're not canceling out. Did we do something wrong? Yeah, that was negative, right? The first term was a minus. So this was actually a minus. Okay, so this is like saying p1 minus p1, which cancel. This term will cancel out with this one. There's a plus p1 squared and a minus 2p1, so we'll be able to do something with that. There's a minus cp1 and a plus cp1, so these will cancel out. So that'll give us, so p1 squared minus 2p1 squared will be a minus p1 squared, and a minus minus c is a c. So c minus p1 squared, right, will have to be equal to 0. Okay. Well, that's just saying P1 square must be equal to C, which means that P1 has got to be equal to square root of C. And we had a relationship we'd established between P2 and P1, which was that, So now the solution that we're doing, all of this is at the optimal point. So the P1 we're talking about now is the optimal P1. So it's saying that in order to get a throughput for the first user of C, that user must transmit at square root of C. Moreover, for it to get that throughput, P2, which is related to P1 as 1 minus C over P1, remember this, will be equal to 1 minus square root of C. Okay. And if you notice between these two equations, P1 star plus P2 star is equal to square root of C plus 1 minus square root of C is equal to 1. And this is independent of C, right? Which was just our throughput for the first user. So no matter what that first user's throughput is, you're going to get that at the optimum point, P1 star plus P2 star will be equal to each other. But depending on what that throughput is, that actually determines what the value should be. And if you go back to our picture, it also matches with our few points that we knew about. So at this point, the throughput for the first user is 1, and the probability with which it transmits is square root of 1, which is 1. At this point, its throughput is a quarter, and the probability with which it transmits is the square root of a quarter, which is a half. Over here, its throughput is 0, its probability of transmission is square root of 0, which is 0. So at all of the other points here, you just transmitted the square root of the corresponding x value. That's what the first user should do. The second user should just do 1 minus that. So that's the throughput for the first user. What's the throughput for the second user? Well, our equations will tell us that, because now we know P1, we know P2, so we can figure out the throughput for the second user. So T2 is simply P2 times 1 minus P1, right? So at the optimum point, at the boundary for a fixed value of T1, whatever you know about P2 and P1, we can use to infer T2. So P2, we said, is 1 minus square root of C1, C. And P1 is square root of C, right? And so this is T2. Okay. Well, what is C? C is just T1. So T2 equals 1 minus square root of T1 square. But that, if you notice, is a fancy way of writing square root of, so if I take the square root of both sides, so I have T2 equal to 1 minus square root of T1 whole square. That means if I take the square root of both sides, square root of T2 equals 1 minus square root of T1, which implies that square root of T1 plus square root of T2 equal to 1. Okay? And this is true at the boundary. What I mean by that is we got all of this by solving this problem. And this problem is maximizing T2. So this is the solution we get if we are trying to find that curve. So that curve then, where you plot T2 versus T1, this curve is just the curve square root of T2 plus square root of T1 equal to 1. That's what this curve is. Or alternatively, it's the curve T2 equals square of 1 minus square root of T1. Okay. And at every point over here, for any arbitrary value of T1 equal to C, the probability that each source should use would be just square root of C and 1 minus square root of C. And I said before, and we won't prove it, the result that the summation of pi star for I goes from 1 to the number of users equals 1 generalizes to any number of users. Only now, as you saw in your assignment, the boundary is not just a curve, it's a surface. Like in 3 dimensions, it's a 2-dimensional surface, and higher dimensions, it's a multi-dimensional surface. We can't visualize it, but that's what it would be. Okay. So that's slotted aloha and the throughput you get with it. So just to kind of recap, what's the benefit of slotted aloha? At a minimum, what it's giving you is it's giving you constant throughput regardless of the number of users without requiring any coordination on the part of the sources. And a reasonable question to ask is, can you do better than slotted aloha with a randomized access mechanism? And the answer is yes, and the answer to that is what's used in today's Wi-Fi systems, and that's called CSMA. So CSMA, as the name suggests, the CS stands for carrier sense. Medium access or multiple access. And in carrier sense, as the name suggests, you basically, before you transmit, you first check the channel. Right? And a different way of visualizing how CSMA is different from slotted aloha is to kind of picture slotted aloha again. So in slotted aloha, there's basically a contention happening for every packet. Right? So in slotted aloha, you either have a packet or you have multiple nodes try to send packets and you get collisions, or you get there's nothing happening at all in certain slots, and other slots you get a packet, other slots different transmitters try to send and they collide, and so on. With carrier sense multiple access, the contention happens at a finer grain than a packet. So it's not that you're contending exactly once every packet, but you might contend in slots that are even smaller than a packet. Okay, so that's one way to think of CSMA, is the nodes contend over a small slot of size, we're going to call it delta. When so one thing that can happen is if no one transmits in this small slot, okay, they simply go to the next contention slot. So the small slot is called the contention slot, and repeat. So you try, it may happen, and what you're doing right now is you're trying with the probability P to send the packet. And if you don't win the contention in this slot, you try again. Okay. So before I go further, let me clarify that we're going to look at sort of a simplified version of CSMA called PCSMA. And after we're done understanding PCSMA, we'll relate it to the version of CSMA that 802.11 uses. And the key difference is that in 802.11, instead of using a geometric backoff, which is what PCSMA has, they use a uniform backoff. So which kind of random variable you use to generate your access attempts. Instead of being a geometric random variable, it's a uniform random variable. But conceptually, it's a similar idea. So you're going to repeat it the next time slot. So what can happen in the next time slot? One thing that could happen is 2 or more nodes start to transmit, right? So if 2 or more nodes start to transmit in that slot, in that small contention slot, there will be a collision, and the transmission lasts for a certain number of slots we're going to call PC. For PC, not slots, but PC time. Okay, or not PC, sorry, TC. Okay. So think of this as sort of collision time. So you have a small slot, you toss a coin with probability P. If nobody chooses to transmit, go to the next small slot. If two or more start to transmit, then there's a time period TC for which the collision is going to last. They're both going to be sending their packet. In general, this collision time can be as long as sending the whole packet. It might be that there's no way for them to tell that they're colliding, so they send the whole packet. Okay. That packet, and this is the key point in CSMA, is larger than the contention time. The contention time is some delta. The packet time is something larger than delta. Okay. The packet transmission times are larger than delta. So during time TC, there is no more contention from other senders. So besides the two or more nodes that are actually colliding right now, nobody else is going to transmit during this collision time. And the way in which in CSMA you can ensure that is that before they try to contend again, they will check the channel. And in this case, the channel will be busy because of these colliding packets in the air. And so when those sources check the channel, they're going to find that the channel is busy, they won't transmit. Okay. So there's no more contention from other senders, because when they sense the carrier, they will find it busy. Okay. And what I mean by sense the carrier is that literally at the transmitter end, it turns on its receiver for a small period of time, checks the level of noise on the receiver. If that noise is above a certain threshold, it declares that the channel is being occupied and does not try to transmit, does not try to contend. Okay. But for those nodes that are involved in the collision, they are sending packets till the end of this time TC. That's the assumption. The third case that can happen, so if we go back here to what we're doing, so there are three possibilities. So case one is no one transmits. Case two is two or more transmit. So this is idle. This is a collision. And the third type of thing that can happen is, what else could happen when they contend? Either the channel is idle, or there's a collision on the channel, or only one transmits, which is a success, right? So case three is if only one node transmits, it transmits for time, we're going to call it TS, for successful transmission time. And no one else will contend or try to transmit during this time. And the reason this is true is because they will sense the carrier to be busy. Okay. So there are three different times we introduced in each case. So in the first case, if there's no one transmits in this slot, you'll go to the next contention slot and repeat, and this is after exactly time period delta. If two or more nodes start to transmit, then they will wait a time period TC plus the delta that happened just now for the current set of contention, and that's when they'll try to transmit again. And then in the third case, besides the current contention time delta, there's an additional TS that they wait before the next contention slot starts. So in each case, like how long it lasts is a little different, right? So in the first case, actually for simplicity, we'll say that if you have a collision, that the total time is TC, that also includes the contention time delta. And similarly, TS includes the contention time that you did. So this TS is sort of capturing the whole period of time. So sort of each contention time or epoch, as sometimes it's referred to, lasts one of three values. It lasts either delta time steps or TC time steps or TS. It lasts delta time units if there's no transmitter. In other words, idle. It lasts a period TC if more than one transmitter tries to transmit during the contention slot, and this is the collision case. And it lasts a period TS if exactly one transmitter occupies, which is a success. In general, these parameters are chosen so that delta is smaller than TC, which is smaller than TS. TC might be very small if you can declare very quickly that the collision is happening. And it may be the same as TS if there's no way for you to detect a collision while it's happening. Okay. In practice, it turns out that, and we'll come to it, real 802.11 systems use something called RTS-CTS, which is a request to send, clear to send handshake before they send the real packet. If you have RTS-CTS, what can happen is that you can detect the collision during the RTS-CTS phase before you get into transmitting the actual data. In that case, you can detect collisions earlier. So then TC might be smaller than TS. But there's a bit of a trade-off because now you have to do that handshake no matter what you're doing. And so it's not always switched on by default in access points even. So, okay, so this is the relative relationship of the three. What we're trying to do, what we're trying to get at is what is the expected throughput for this PCSMA. So unlike our previous example where for Aloha all of the packet slots were the same duration, now idle times you can already see don't last very long. That's one benefit of PCSMA. Whereas in the slotted Aloha systems, idle times last as long as packet times. Here, idle times can be much smaller. So this delta is the idle time. Or you can have periodically, more than one node tries to send, and that's a collision. So that would last a certain duration TC. And then maybe you have a bunch of idle slots, and then maybe you have a nice successful period of time when exactly one packet is sent. Then maybe some idle slots, maybe another nice long successful transmission, then maybe some collision that lasted for TC and so on. Okay. So the timeline for PCSMA, for the CSMA protocol that we're talking about, looks a little different from the timeline that we had for slotted Aloha. So in slotted Aloha, whether it was a success period, a collision period, or an idle period, they occupied the same amount of time on the line. Whereas you can see that in CSMA, somehow we're able to so this is sort of a typical Aloha timeline. This is a typical CSMA timeline. And the key difference you can see is that you end up spending more time on the successful periods and less time on idles, and if TC is small, maybe also less time on the collisions. Okay, and intuitively, this should translate to better utilization. So that's the intuition. The intuition is by shrinking our idle times, we're able to get more out of the system in terms of throughput. So intuitively, if delta is much smaller than TS, then the throughput for CSMA should be better than Conversely, you could argue that slotted aloha is just a special case of CSMA in which delta equals TC equals TS. Right? In fact, one can even view as a special case of PCSMA when delta equals TC equals TS. Right? So in that case, whether it was collision or whether it was success or idle, they were all the same duration. So during the contention, so every time you enter into the next segment, nodes are still tossing a coin independently. All of them are transmitting a coin with probability P. They're going to try and access the channel. The only difference now is that when you grab the channel and you're sending it, everybody else knows not to transmit, so they won't collide with you once you've started to transmit. And when you're done sending your packet, then everybody is aware when that is, and now everyone's going to toss a coin again and try again. It might end up being idle, it might end up being a collision, it might end up being a success, and you just keep repeating this process. So if you want to figure out the expected throughput for PCSMA, in some sense what we need to find out is what is the fraction of time you spend in the success state. Okay? And it turns out that the way you do that basically is you find the expected success duration by taking each possible epoch, like the time between contentions, as a random variable, and you say what is the expected duration of this epoch. So, and sorry, not just the expected duration of the epoch, but sort of what fraction of those are successful. So the expected success duration is what we're looking at. So expected throughput turns out to be equal to probability of success times the success duration divided by expected epoch duration. Okay, so the epoch duration refers to time between contention events. Okay, and it's the epoch duration is what we were referring to here. Each contention time or epoch lasts either delta or TC or TS. So this epoch duration, let's give it some name. Let's call it, I don't know, let's call it, let's just call it E. This epoch duration E is not always delta, it's not always TC, it's not always TS. What type of a variable is it? Is it a deterministic variable or a random variable? It's a random variable. So the epoch duration is a random variable. Is it a continuous random variable? Is it a discrete random variable? In general, it could be continuous. But in the model that we're adopting, every transmission lasts exactly TC. Every collision. Every successful lasts exactly TS. Every idle time lasts exactly delta. So these three are just three particular values. And so the epoch duration can only take on values delta, TC, or TS. So it's actually discrete. There's only three possible values. So it's a random variable that takes on one of three values. The PMF of this random variable, because it's a discrete random variable, we can talk about its PMF, will depend on what happens during the contention. Do you have that nobody wins out? Do you have that exactly one person wins out? Do you have that more than one? So those probabilities are associated with each of these three values. Okay. So the PMF of the epoch duration is as follows. It's equal to delta with probability that nobody transmitted. So that's 1 minus p to the n. So nobody transmitted. It's, let's do TS next because it's easier. Is exactly one of them transmitted and the others did not, which happens with probability n times p, 1 minus p to the n minus 1. Similar to what we said about slotted aloha. And TC happens with the probability that's 1 minus p to the n minus np 1 minus p to the n minus 1. So this expected throughput, which is the probability of success times TS, you can think of this as the expected, this is like the fraction of time that you're spending in successes, is the fraction of times it is successful times how long a success period is, divided by the total period, right, in expectation. So this equation, by the way, is not an obvious equation. It seems intuitive, but if I take into account the fact that the epochs are actually random variables, I mean their duration is a random variable, and I'm tossing these coins with some probability, I end up getting a success, and that success lasts a certain period. This expression comes from a theorem in a branch of probability known as renewal theory, and is a consequence of something called the key renewal theorem. So mathematically deriving this expression is not a completely trivial fact. I mean, it seems very intuitive and very reasonable, and in fact, if you were to calculate it this way, you would get the right answer. But why is the statement true actually comes from a certain theorem in probability that tells us that if you have a process of this type, where at every beginning of each epoch, you're sort of renewing the process. It's as if it doesn't matter what happened in the past. Right? And what's happening in each epoch is sort of independent of what's happening in every other epoch. And long term, what I'm interested in saying is what is the fraction of time I'm spending in successful packet transmissions? That's my throughput. And if I want to figure out my expected throughput as the long-term fraction of time spent in this doing something that's the successful transmission period, the way I can compute that is to focus on each epoch separately and say what is the expected duration of the epoch, put that in the denominator, and say what would be the expected duration if it was successful, put that in the numerator, and take that ratio, that's going to be the expected throughput. This statement is not an obvious statement. But you can derive it, and it'll boil down to the key renewal theorem. So we're not going to do the derivation of it. I'm just pointing out that this expected throughput expression for CSMA is a little bit more complicated than it was for Aloha. The difference is that in Aloha, all of these durations were the same length. Then it was just a question of what fraction of your slots are reception slots, right? Then you're done. Here, not only do you have to say what fraction are successful, you also have to take into account how long they are in each case. Sometimes they're long, sometimes they're short, right? And so it's a little bit more than just counting how often you're successful. You also have to take into account how long is it when you're successful, and when you're not successful, on average, how long is it? So that's why this expression is not simply like, you know, if we had just slotted Aloha, you simply count how many times are you in collision, just take the probability of that and you're done. In success, and take the probability of that and you'd be done. So it's a little bit more complicated. So as a result of this statement and our PMF of the epoch duration, so the numerator is kind of the probability of success, which is the same as this, right? But to find the expected epoch duration, we need to find the, this is the PMF, you know, let's call it P for the epoch duration. So this PMF for the random variable E gives us the expected value of E also, the expected epoch duration. So that'll be with this probability delta plus with this probability TS plus with this probability TC. That expression is going to go into the denominator. Okay. So now let's write out the expected throughput. So this is going to look pretty messy, but let's write it. So the probability of success is n times p times 1 minus p to the n minus 1 times ts. The expected epoch duration is with probability 1 minus p to the n delta. It is with probability n times p times 1 minus p to the n minus 1, it's ts. And with probability 1 minus p to the n minus n times p times 1 minus p to the n minus 1, it's tc. Okay. So this whole expression is going to be our expected throughput now. Now the challenge with this expression compared to the slotted aloha expression is that it's not so easy for us to, it can be done, but it's not easy for us to get a clean expression for, or take derivatives and set them equal to 0 and solve for the optimum value of p. And in fact, you don't get a clean expression for p. It's something, pretty messy looking. And we'll come back to what that expression itself would look like. However, if you were to actually take values of delta and ts and tc, solve for the optimum value of p in those cases, and then plot it, you would get the optimum transmission probability as well as the corresponding throughput. For now, before we do any sort of numerical calculations with it, let's kind of just look at this expression and see why it might be, what kind of insights one might get out of it. So one thing you can see already is that if Tc and delta were negligible compared to Ts, right? If delta was really small, Tc was really small, then the denominator expression, these two terms would sort of shrink accordingly. And what would dominate in both the numerator and denominator would be this term, and would get closer and closer to 1. Right? So this already you can at least, from the throughput expression, you can see that what determines a lot of the utilization is the duration of the idle and collision times. So if those could be reduced with respect to the success time, you would get better performance. So in general, this gives us the insight that as Ts gets larger compared to delta and Tc, the throughput increases. And you have to be a little careful because it will only do that. You're really talking about the throughput at the maximum point. Like as you're optimizing with respect to P, you find the optimum P. But to find the optimum P, it's for a particular combination of Ts and delta and Tc. So it's at that optimum point, but intuitively as you keep increasing Ts, this term will be always the dominant term, is going to tend to do well. And that's one big difference between PCSMA and slotted aloha. So slotted aloha, as n gets larger and larger, you sort of end up saturating your maximum throughput at about 36%. With PCSMA, if I was able to keep increasing my success duration by having larger and larger packets, it turns out I can get arbitrarily close to 100% throughput. In fact, CSMA, when I have extremely long packet durations, arbitrarily large packet durations, will tend to close to 100% throughput. Seems very counterintuitive, but the intuition is that when I'm successful, I can take the channel for long periods of time, then I only waste time when I'm contending. Okay, and if those time periods, each of them is very, very small, they will pale in comparison to the benefit I get when I do grab it eventually. So I have long periods of collisions, maybe idle periods, but the moment I get the channel, I get occupied for a long time. That improves my efficiency. So overall, the throughput sort of benefits if I have a larger packet size in this case. So for CSMA, typically it takes some simulations to be able to build intuition. So let's see if we can look at an example. I'm noticing that they have Matlab on this computer, so if I can pull it up, we can just code this in and see. we switch to the this computer, please? Let's see. Okay, good. So let's try a simple example with just 2 users. So we're going to set n equal to 2. And let's first kind of plot that throughput for a range of probabilities. So let's just take, I don't know, let's take 10 values of p going from 0 to 1. And let's choose some values for delta, ts, and tc. So delta I'm going to call d. Let's make that 1, just normalizing it. Let's say tc is, I'll just pick some small value for now. And let's say ts is large comparatively. Let's just say 20. Okay. So this throughput equation that we have that we want to program in is, oh, and what did we say for n? We do have that already. Okay. So let's just say throughput equals n times p times 1 minus, oh, this has got to be a vector. Okay. In fact, let me do it in 2 steps. So let's call it t, the numerator is n times so that is what it is. And then the denominator term has that in it, and then on top of that has other terms. Yeah. Oops. P 1 minus P make sure I'm matching my parentheses here times TC. So I forget if I started with the parenthesis. I hope I did. Okay. So that's my denominator, and so oops. What did we call this? Just throughput? So here's the plot that we're getting for throughput in this particular case. I hope I didn't make any data entry errors, but this is the particular curve that we get. Here the x-axis is the access probability p, the y-axis is the throughput, and one thing that's immediately apparent is that the maximum throughput for whatever p star it is much higher than 36%. In this particular example, it's close to 90%. Right? And of course, that's a function of my choice for D and TC and TS, and I purposely chose a TS value that was very high. It was close to 20, whereas D was only 1, and TC was only 3. And in the equation that we looked at, you can kind of see why there's a robustness to P, is that regardless of what P is, if TS is really high, it's going to tend to 1. Unless if P was really, really small. So what happens when P is really small is that you're not transmitting very much, in which case that idle term is going to be, I mean, in this case it actually is 0 because I only chose points 0.1 apart. If you have transmission probability 0, nobody's sending, your idle times are probability 1, all of the other times of 0, so it ends up having utilization of 0 in that case. Likewise, in the other extreme where you're always sending, everybody's always sending, the term corresponding to collisions has probability 1, or very close to 1, and so that term ends up dominating. Right? So in those two extremes, you do have low throughput, but in between, for other values of P, that middle term starts to dominate, and that gives you the improvement in performance. So there's sort of a little bit of intuition about why this might be happening. So here n is just 2. This is just 2 users. You might say that's kind of small. So let's try n of, I don't know, 4 or something. Hopefully the equations will stay as I entered them. So let's go to tune numerator. That I think was the denominator. So now we are doing with 4 users, and you can see that the curve is a little bit differently shaped. The peak probability has shifted a little bit to the left. This happens also in slotted aloha. As you increase the number of users, P star decreases as 1 over n. So you get less and less aggressive as you get more and more users. And on the right side, you'll see this tapering off effect. Now we have 4 users rather than 2. The tapering off effect is because now the collisions are much more likely on the right. So in any of these slotted aloha or CSMA curves, the reason it goes up initially is you're starting to utilize the channel. When it's too far to the left, it's too idle, right? But then after you hit the maximum point, it starts going down because of collisions. And as you increase the number of users, that probability of collision starts to increase, so the right-hand side is going to get more and more sort of sharp. But it's still interesting to note that your maximum throughput point is pretty high. So if you were choosing your optimum value, you're still able to get close to 90% in this case. Of course, if you changed your TC or TS accordingly, that would affect performance. So we had over here, we chose certain values. Let's choose, something where collisions are pretty long as the success times, and the success times only 5 times the idle slot. You would expect maybe some impact on the throughput because of this. So let's see if that happens. So here you see, as we decreased the success time, that the maximum throughput got cut down from 90% to a little bit above 60%. So this does have an impact on performance. But in general, if you could increase that ratio of TS to delta, you're able to improve performance. So that's sort of one of the takeaways from looking at PCSMA. So any questions about the difference between slotted aloha and PCSMA? So the throughput benefit is now being derived by the fact that when a packet is in the air, there's no contention happening. And the contention periods are reduced so that they don't, if things are idle, you don't waste time. You can get back to trying again right away. You don't have to wait a whole slot. So both of those are the big reasons why it does better. So can we go back to the overhead, please? Okay. So if we look at PCSMA, just like we did for slotted aloha, you can extend it to a PI CSMA, right? Why might you do that? So first of all, what does PI CSMA mean? Is that each, so transmitter I chooses to contend with probability PI during contention slots. Right, so instead of everybody choosing the same probability, you might give a different probability to different users. Why might you do that? Higher priority. And the same reasons we were doing it for PI slotted aloha, which is you may have scenarios in which there are different transmitters. They're trying to use different applications, and some applications need more throughput than others, and so are higher priority than others. And you might want to give some users a higher probability of access than others. So the idea is very similar to analyzing the throughput region for slotted aloha, except now the equations are much more complicated. It's harder for us to just derive in closed form what will happen. But intuitively, just as for P slotted aloha, you had one point that's the optimum point, but for PI slotted aloha, you get a whole region, and there's a boundary of that region. There's a similar thing that will happen in PI CSMA as well. So now the key difference is that that curve is going to be looking a lot better than the curve we had for slotted aloha. Now with PI CSMA, even when they both have roughly the same values of P, before it was like their maximum throughput was for two users like a half. Now it can be potentially very high. It could be even close to 90% depending on the throughput. So each of them might get a value that's instead of a quarter, it might be closer to a half. So this curve for CSMA is going to start to look more and more like a straight line. Like the best you could hope for any region, right, between would be a straight line, because a straight line would represent perfect time sharing. Where T1 plus T2 equals 1. So whatever throughput you have on that link, you can give exactly a fraction to T1 and the rest of it to T2. Right? Slotted aloha does something like this, we just saw. But CSMA ends up getting curves that are closer to the ideal line, and it'll get closer and closer to that ideal line as the success time is increased. Okay, that's basically what ends up happening. And just like we have that condition that the sum of PI stars must equal to 1 for slotted aloha, there is a similar condition, a generalized condition for CSMA that must hold at the optimum point. And the student who took this class in 2010 or 11 asked basically that question in class. He ended up working with me for a semester doing DR, and he came up with an expression that he conjectured for what that condition should be, and then we proved it and published it the next year. And I think I might have mentioned before, it turned out that just a couple of months before somebody else had published the same result. But it was a pretty nice result to come out of this class. But it's showing that many of the things we see in slotted aloha also happen for CSMA in general. It's just that slotted aloha is a special case of this bigger problem. So I'm going to show you what that result looks like. Hopefully I can bring up the paper. Could I have the computer and the projector, please? So this was the paper that we ended up writing based on that student's work. So a couple of things here to show you. One is the curve itself that we were just discussing. Here. So this is the boundary of the two-user saturation throughput region for P-persistent, sometimes called P-CSMA or P-persistent CSMA. So T over sigma here is like our TS over delta. Okay. So if TS over delta equals 1, that's slotted aloha. That's this curve. That's the curve we've been talking about. And if TS over delta is 10, that's this blue curve. As it gets higher and higher, in this case close to 100, you can see it's almost looking like that straight line connecting these two. Right? So that's what we were just saying. This figure shows the condition relating P2 and P1 at the optimum boundary of the throughput region. This line is the line for slotted aloha where P1 and P2 must equal to 1. Right? But it turns out that as the success time to idle time ratio gets higher, there's a different relationship that they must follow that ends up looking more and more kind of lower down. So for small values of P1, it's a much higher value of P2, but as P1 gets larger, P2 drops much more. So basically, there's a different condition that you end up with. But of course, the special case of slotted aloha is the limiting case when TS over delta goes to 1. And I'll provide a pointer to this paper if anyone's interested. The general relationship, which I will note down here, is this equation. And in this paper, we made a simplifying assumption that TS and TC are equal to each other and equal to T. And the notation here for delta is sigma, so it's the same thing. So there's another condition that's derived for the optimum choice of the PIs. That if they satisfy this equation, then for every user, then you're at the boundary of the saturation throughput region for CSMA. So that was sort of the main result of the paper. So could I go back to the overhead document camera, please? So let me just write down that equation. So at the what's called the Pareto boundary of the saturation throughput region, of piece or PI CSMA, the following condition holds. So we call it delta, I'll leave it at that. Assuming TS equals TC equals T. And even if this condition didn't hold, you could derive an expression, it just gets a little bit messier. But then this equation can simplify further as so if I were to rewrite this expression, I could rewrite it as T over delta. So I can cancel out these 1 from both sides. This negative term can go to the other side. So we could get this as well. Okay, here's a simpler expression. So this expression looks in general a little bit more complicated than the expression for slotted aloha, but as we said before, when T over delta equals 1, this is just slotted aloha. So we should recover back the condition we know that they should add up to 1. And we can verify whether that's true. If this was 1, then you get summation of pi plus product of 1 minus pi minus 1 equals the product of 1 minus pi. These two terms cancel out. You get summation of pi minus 1 equals 0. Summation of pi equals 1. Right? In this case, the above simplifies to summation of pi equals 1. But in general, it's a little bit more complicated. So again, just a comment on what these throughput regions really mean. So if I have some throughput for one user, some throughput for the other user, I can always achieve some point in the interior, let's say by some combination. And the claim is that there's no benefit to operating in the interior, right? because what the existence of the curve above tells us is that there's some other point where I can get, for the same throughput for user 2, a higher throughput for user 1, or I can keep the same throughput for user 1 and give a higher throughput to user 2. So at a minimum, either of these 2 points is preferable to this one, right? In fact, every point in here is preferable to this one, because at every point in here, throughput 1 is higher than you're getting here, and throughput for 2 is also higher than you're getting here. So in fact, all of these points are all better off than this one, right? And so this boundary, and I've used the word Pareto, okay. What it really is a set of points that are not, I'm going to use this phrase, dominated by any other throughput vector. In other words, if I was on this boundary, though, there's no way to say there's a better throughput I could achieve for both of them simultaneously, or for one while keeping the other one fixed. So in some sense, comparing along this curve, that's like comparing apples and oranges. Like if I ask you, is this point better or this point better? Well, it depends on your application, right? But is this point better or this point better? It's clear this point's better. It doesn't matter what your application is, right? And so that's the notion of Pareto boundaries, is that they tell you, regardless of what you care about, certainly you must care about something here rather than something in the interior. And that condition we were just talking about ensures that you stay on the boundary, because there's no benefit to being in the interior. You want to stay on the boundary. These conditions tell you that you should tune the probabilities accordingly. Okay, so that's sort of the key insight we're trying to derive and take away from all this. Incidentally, the idea of PICSMA is also implemented in real systems. So the standard 802.11 variants that we use in our laptops, like 802.11, G, P, and all of those, not P, sorry, G and N, for example, B before that, all basically use a version of CSMA that's similar to PCSMA in that everybody has the same parameters. They all have the same access probabilities. But there is a variant of 802.11 that was proposed to allow for quality of service, different quality of service for different applications, that's called IEEE 802.11e. And this was basically for wireless LANs with QoS. And in the 802.11e standards, different applications can use different access probabilities. Okay, maybe I should put this in quotes, because it doesn't, unlike PCSMA, it doesn't just toss a coin with the probability P each time. It does it using a uniform back-off window, but the size of that back-off window basically determines how aggressively you're transmitting, similar to how the probabilities in PCSMA affect your aggressiveness of transmission. So I'll talk about the kind of realistic variation of PCSMA that gets implemented in just a second. But at a high level, standard variants like IEEE 802.11a, B, G, N use the same access probabilities for all sources. So these are kind of based on PCSMA. These are kind of, this one's kind of based on PICSMA. So the difference from PCSMA and how it's implemented in IEEE 802.11 standards is there's sort of two basic differences. The first difference is that instead of choosing to access with probability P at each slot, So if you choose to access with probability P at each slot, the number of time steps until you actually try to send a packet, that's geometrically distributed, right? So why is that geometrically distributed? It's like tossing a coin and waiting for heads. If I toss a coin and every time it's probability P of coming up heads, the number of times until I see the heads, that's a geometric random variable. So instead of doing this, as in PCSMA, in 802.11, the access time is chosen to be a uniform random variable. So in practical implementations, having a geometrically distributed access time is a little worrisome. The biggest worry is that it means that in the worst case, it can be arbitrarily large. There is no maximum size to the access time if it's geometrically distributed. You can have potentially, if you look at the PMF, it can be, 1 contention slot, 2, 3, 4, all the way up to infinity. You might have to wait infinitely long with very low probability, but there is a probability. Whereas if you choose it to be uniform random variable, there's a minimum, in this case 0, and a maximum, whatever that is. And so your maximum time you might have to wait is finite. Right? So this guarantees a finite. Secondly, it's easier to implement, pick a uniform random variable between 0 and whatever the maximum value is easier than having to constantly pull random numbers each time. So from an implementation point of view as well, it's less complex. Okay. So that's the one big difference. So uniform random variable from, chosen from the interval 0 to some maximum, let's call it, where B is called the back-off window. Actually, W. I think we'll use W. The second thing that's different about 802.11, and we'll get deeper into it in the next class, I'll get started on it, but we may not complete it today, is that the back-off period or maximum size of the window, or let's say the size of the window, is increased each time there is a collision. Okay. Specifically, it's actually doubled up to a maximum. So there's two things happening now that's different from P-persistent CSMA. So P-persistent CSMA, it would look like this. You have a bunch of transmitters, and every time they're contending, they toss a coin. If it comes up heads, they will transmit. If it's not, they won't, right? And before they toss the coin, they check the channel to make sure that it's not occupied. With 802.11, again, just the same way, they will first check to make sure the channel is not busy. If it's not busy, they will transmit. But not with the probability P, they will transmit if a certain counter has counted down to 0. This counter is chosen at some point as a uniformly random variable from this value 0 to W minus 1. Okay. And so you count, so you pick a number from 0 to W minus 1. That many contention slots you will not transmit. You'll keep decrementing the value. When you hit 0, then you transmit. Okay. So every time you transmit, you check whether that transmission was successful or not, whether you receive an ACK or not. If there's a collision, then you're going to double. For the next time, you're going to pick a random number, not from 0 to W minus 1, but from 0 to 2W minus 1. Okay. And again, whenever you count down to the 0 value from this random number that you generated, when it comes down to 0, you'll transmit again. And again, you check if it was successfully received or not. If it is successfully received, then you're done. You start the next back-off window from the original initial back-off value. Every time there's a collision, though, you'll keep doubling it. So we'll go from W to 2W to 4W to 8W and so on until you hit a certain maximum size. When you hit a maximum size, you kind of keep it at that value, and then you keep repeating. So this part of it, where you adjust the back-off period to the collisions, that's something that's done in 802.11. We don't see that in the PCSMA. There's a couple of reasons for this. One is that your initial back-off window might be kind of small, just to kind of reduce your deterministic latency if there are no collisions, if there's no interference. On the other hand, because it's a finite number, if that number is too small, you'll keep colliding. Chances are very high that you'll keep colliding. And so by allowing for this probability, for this possibility, you're almost kind of balancing in part for the fact that it's a finite window. So you might need to make that window larger to avoid collision. So that's what this is doing. On the other hand, the other benefit you get from this is that that sort of window is only increased when you're seeing a lot of collisions. So if the number of users is varying over time, sometimes you have heavy traffic, you have a lot of users, other times there's virtually no users, then it sort of adapts the amount by which you're backing off accordingly. So when there's not a lot of users, you're not backing off by very much. You're very quickly accessing the channel. When there's a lot of users, very quickly you will double your windows to the large back-off window size and try to pick timings from that to reduce the chance of error. So the second part of it is sometimes called binary exponential back-off. Binary exponential because you're doubling each time. You're exponentially increasing the size of this window each time that there's a collision. So in this type of 802.11, essentially you can think of having different stages. Right? So you start with stage W0, then you go to stage W1, all the way up to some WM. And then if you're at this stage and you're still seeing a collision, you don't increase it anymore. You kind of keep it there. But every stage is twice as large as the previous stage. So W1 is 2 times W0. W2 is 2 times W1, which is 2 to the 2, W0, and so on. It'll just be 2 to the M, W0. Right? So each time you keep doubling. W0 is the initial, it's called the initial back-off window. And this is the maximum. So what we'll see in the next class is that the behavior of 802.11 medium access, that CSMA, for every stage, you can kind of represent it as having a set of possible values for the timer, anywhere between 0 to W0 minus 1 for that 0th stage, all the way up to anywhere between 0 to WM minus 1 for the last stage. Those are all the values that the back-off counter can take on. And every time you go to the next stage, you pick uniformly from any of those possible values, and you keep counting down. And eventually, when you hit 0, you transmit, and if you're successful, you go all the way back to the 0th stage, right? And this whole process of switching between different states, depending on whether there's been a collision, and decrementing those back-off counters at each time, can be modeled by a Markov chain. Okay, so basically, you can model the back-off counter. This is basically the counter that is decremented from that initial random variable that you pick. So what we can do is we can model this back-off counter's value along with the back-off stage as a Markov chain. And in the next class, we'll see that we can basically write this Markov chain if I tell you the parameters that are chosen in 802.11, which is the choice of W0 and M. These are the only two parameters. Right? So given W0, given M, given the number of users, given the, oh sorry, no P now. Given the number of users, we can, TS, delta, TC, we can calculate the saturation throughput for IEEE 802.11 max standard. And we'll do this, go over how the theoretical expression for this is derived using the Markov chain, and your project in the next week will be to take the theoretical equation we get from doing this and run NS3 simulations of 802.11, plot the two curves and see how well they match each other. So one will be sort of completely mathematically derived. The other will be what you actually observe by simulating 802.11. And you'll be able to compare the two. And the person who came up with this analysis, his name is Giuseppe Bianchi. So we'll look at this analysis. And this analysis dates back about I forget, about 2000, early 2000s or so. Late 1990s, and that analysis has really helped us understand how to design MAC protocols and how to optimize them for different applications. So it's a very fundamental result in the theory of wireless networks. So we'll see that next class. Okay, we'll stop here.